Hi, welcome back to the Cosmic Classroom. So we'll now talk about neutron stars, which are the result of the evolution of very high mass stars. So if the star has enough mass, it will fuse hydrogen into helium, then helium into carbon. It keeps going on and fusing heavier elements and getting energy out of that. But eventually it forms iron. And as we talked about before, you can't get energy out of fusing iron. So at that point, the star can't get energy to balance the gravity that's pushing on it. And the star then collapses. Well, when the star collapses, so you have this iron core that then is too cold. It becomes a little bit too cold to be able to stop the gravitational collapse. And then gravity wins and it collapses. Well, when this core of iron collapses, the electrons combine with the protons to become neutrons. So you lose the information about what kind of atom there was there before, and instead there is this big ball of neutrons. So the density is the same density as you would find in the nucleus of an atom. Those are extremely high densities. So in this case, what stops the collapse from going even further is what's called neutron degeneracy pressure. It's the neutrons are so close together that you can think about it as they're physically touching each other. And that's what's stopping them from collapsing even further. But it's extremely dense. It's very, very hot because as soon as you see it, because after all, it's the core of this very high mass star. And the temperatures that were needed to fuse something into carbon were very, very high. Now, if you thought that white dwarfs are extremely dense, and they are, neutron stars are, to blow your mind, how dense they are. So in order for you to have an idea of the density of a neutron star, imagine getting that same table, the same teaspoon that we got before, and we imagine in the white dwarf that we would pack about 100 people in there. Now imagine instead getting the entire population of the Earth and packing it in that volume. That's how dense a neutron star is, okay? It's unimaginable, right? It's very, very dense and hot. So a neutron star is sometimes observed as a pulsar. So a pulsar is a neutron star that's rotating very fast and emitting light in just one direction or in two directions. So for example, in the slide, you have a couple nice drawings here. So in the drawing here on the left, we have a neutron star. The neutron star is rotating extremely fast because of conservation of angular momentum. We started with this huge, massive star that was rotating. Well, as the star collapses, the angular momentum needs to be conserved, and the star spins really, really fast. The star spins really, really fast. With that, there is the magnetic fields become even stronger than what they used to be in the surface of the high mass star. And the star starts to eject light in beams, in two beams. Very similar to what happens in a lighthouse, very similar to what happens in a lighthouse. Pulsars can spin so fast that they can spin many times in 1 second. And when they were first observed, they were actually first referred to as LGM, for little green man. Because nobody could understand how something could be creating a signal that was so fast and so uniform, so constant. So for a while people thought, oh, maybe there are some aliens out there trying to contact us and creating this signal. But pretty soon it was realized that that wasn't the case. So you can think about hearing a neutron star. Instead of, you wouldn't be able to see the neutron star blinking, because it emits this jet of radiation mostly in the radio, and your eye cannot see radio. But you could assign a beep every time there is a peak of intensity of light, and then you could hear a pulsar. So here's an example of hearing a pulsar. So every beep you hear is correspondent to an increase in the intensity that you observe here from Earth. So for example, this one, it rotates 1.4 times each second. About the crab pulsar, it's 30 times per second. And it's really hard to discriminate there. But actually, there are pulsars that are even faster than that. 627 rotations per second. See if you can hear that. All right, that at least woke you up in case you got a little bit bored. All right. Now, you don't always observe a neutron star as a pulsar. It depends on your location. If you're in a good location, you'll see it as a pulsar. If you're not, you won't. So let me show you this movie in which you'll be seeing the pulsar from different locations. From some locations, you'll see it getting brighter and dimmer, and from others, we won't. So let's see it here. Now you're seeing it from the side. So if you were to measure all the luminosity coming towards you, it wouldn't be changing. Notice the blue lines are the magnetic field lines that you can't really see. It is just a drawing. And there you go. Now it's going right at your face, and you would see it being brighter, 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 and brighter. And each one of those would correspond to one beep that I just showed you. Okay? Another way to think about it is I can pretend to be a neutron star. So let me say that I have two jets, one going that way, one going this way. Okay? And if I'm rotating and if my arms are going this way, you will see it, and then you won't, and then you will, and then you won't. Now, if I were inclined like this, maybe you wouldn't see me as a pulsar at all. You would just see me as a neutron star. The brightness would not be varying. So it's just a question of geometry. It's just a question of where you are located. Now, I got a really good question from a student this week about neutron stars. And I had to scratch my head a little bit. Professor, how come we have such strong magnetic fields in a neutron star? After all, neutrons are neutral. They don't have charge. And I know that in order to have a magnetic field, I have to have moving charge. Excellent point, excellent questions. A neutron star is made mostly of neutrons, but not completely, okay? So if you really look in detail in the structure of a neutron star, you'll see that there are also superconducting protons in there. There are also ions, and there are also electrons, okay? So it's not just one big ball of neutron. It's one big ball of neutron with some charge attached to it. So just to finalize, we sent two spacecrafts into space in the 70s. Those were called Voyager 1 and 2. They are about to leave. They actually left the solar system. They already traveled through all the planets, went through Pluto, all the way getting out of the solar system. And in there, we put two gold plates, one in each one of those spacecrafts. So the idea is that those plates, if ever grabbed by an alien civilization, will know about us. We'll be able to tell them, hey, we are alive here on this planet. So there's a lot of information in there. We tell them how we know about the structure of the atom. We tell them that we know about light. So there are many different things there. And one of the pieces of information is a map to help the aliens find the sun. So The map is based on the location of pulsars all around us. The idea is that if the aliens are smart enough to have mapped all the local universe and know all the location of all the pulsars, they should be able to get to us. And that's it. I hope you know a little bit more about pulsars and neutron stars.